This lecture is on chapter 2.8 to 2.9 and 2.11 to 2.14 on electron configuration and atomic radius. So we've now determined what orbitals are and how they arrange energetically. Now we have to figure out how do electrons actually fill those orbitals. So electron configuration is a description of which orbitals are occupied by specific electrons. And so the ground state electron configuration is the lowest energy configuration of electrons within those orbitals. So the buildup of electron within orbitals follows the off-ball principle, which is basically the principle of building up. So it's a set of guidelines for filling these orbitals. So the off-ball principle has three different tenets. So the first is 1, lower energy orbitals fill before higher energy orbitals. 2, an orbital can only hold 2 electrons, which must have opposite spins. We'll get into spins in the next slide. And if 2 or more degenerate orbitals are available, 1 electron goes into each until all are half full. The electrons in the half-filled orbitals all have the same value of their spin quantum number. And so this third part is called Hund's rule. And so the reason for that is it decreases electron-electron repulsion. Okay, so all this discussion of spin, what actually is electron spin? So we have the 4 quantum numbers in the last lecture that describes each individual orbital, the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. And so now we're going to introduce a fourth, and so each of those set of 3 quantum numbers describes each individual suborbital that an electron can reside in. Now there's a 4th quantum number called the spin quantum number, so m sub s, which talks about which spin orientation each electron will have. So the Stern-Gerlach experiment shows that in a magnetic field there are 2 types of electrons, a spin up and a spin down. And so we identify which direction of spin happens by the spin quantum number m sub s as a value of either plus 1/2 or minus 1/2. And that corresponds to either spin up or spin down. And so this is defined by the spin direction of an electrode. And so back to our sort of dorm room analogy. If we talk about your dorm room as a specific suborbital, if you're talking about which of the 2 electrons within that suborbital you're talking about, that would be like talking about which bed in your dorm room. If there's 2 different beds, one for you, one for your roommate, we could say one is for an electron that spin up and one for that spin down. Okay, so the set of 4 individual quantum numbers, the n, the l, the m sub l, and the m sub s, actually describes each individual electron within an atom. Okay, and so the spin up and spin down. So I don't know in physics before if you have ever had had a discussion of the direction of a magnetic field when there's a spin. And so it's the right hand rule here. So when you cup your hand and spin it counterclockwise, your thumb faces upwards. And so that means that the spin direction is the net magnetic field is upwards. Whereas if you turn your hand upside down and then spin your hand clockwise, your thumb faces down. Okay, and all of this spinning was with the right hand. And so that means that our direction is downward. And so that is the direction of upward or downward spin. Talks about the magnetic field depending on which direction that electron is spinning. So as I said, together these 4 quantum numbers describe every electron within an atom. And so the Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers. Okay, so even though there's 2 electrons that can reside in each of these suborbitals, each of those electrons are going to have opposite spin. So if we're talking about an electron going in this 2s orbital, one's going to have a spin in one direction with a plus 1/2 spin quantum number, and the other one's going to have a spin in the opposite direction with a minus 1/2 spin quantum number. Okay, and so electrons are going to fill based on that off-ball principle from lower energy all the way up to higher energy. They're going to pair up with 2 electrons per suborbital. And if you have degenerate orbitals, they're going to fill one at a time in a spin direction that's all the same. So, for example, in the 2p would fill face up, face up, face up before they start to pair face down, face down, face down. Okay, and this will become more clear in a slide or two. Okay, so if we recall back to the Balmer-Rydberg equation, where we talked about the equation that defined the wavelength associated with each of these individual lines, each of these energetic electron transitions, where we talk about the M and the N talking about the energy level in which an electron came from, or the energy level in which an electron is going to. Okay, so now that we have a better understanding of the electron orbital diagram, you can have a better understanding of where this Rydberg or Balmer-Rydberg equation is actually coming from. So these are talking about electrons that are located in these energy levels. And so these M and N turns are talking about our principal quantum number. So our energy level, whether it's 1, 2, 3, 4, 5, et cetera, et cetera. Okay, and so transferring between these energy levels gives us our N and M term. Okay. Okay, so now how do we actually put in our electrons into an orbital filling diagram? So there's three different methods of expressing electron configuration for an atom. And so let's use nitrogen as an example for the atom that we're going to be talking about. So if we look on our periodic table, we can see that nitrogen has an atomic number of 7. So that means for a neutral nitrogen species, we're going to have 7 electrons. So there are different ways for us to talk about how these electrons configure. And so let's take a look first at the one on the very bottom of this list, which is an orbital filling diagram on an energy scale. So if we draw, so nitrogen is a multi-electron element. So we draw it with the staggered sort of design. So we have 1s on the bottom, then 2s, then slightly up, 3 degenerate orbitals for 2p. Then we go to 3s, 3 degenerate orbitals for 3p. And then remember, next goes to 4s. And then we go to 1, 2, 3, 4, 5 for 3d. And then 1, 2, 3 for 4p. Okay, so if we have 7 electrons for nitrogen, we follow the off-ball principle here, saying we start from lowest energy level all the way up. Okay, and so we put our first electron, 1, and then we have to pair this up. So spin up, we put an arrow going upward. So that would have a spin quantum number of +1/2 because it's going upwards. And then we're going to pair them up with a spin going down. So that guy's now going to have an M sub s spin quantum number of -1/2. So that's a paired up set of 2 electrons into that 1s orbital. So 1, 2, then 3, then 4. And then now we're going to fill this 2p degenerate orbitals here, and we're going to fill these 1 electron per suborbital, one at a time, all with the same spin direction. So we've already put 4 in, so we need to have 3 more electrons. So we go 1, 2, 3 electrons. All of those guys are all going to have that same upward spin quantum number. Okay, all that upward spin direction. And so we can use our set of 4 quantum numbers to actually define any specific electron within this filling diagram. Okay, so on the bottom of the list here, the orbital filling diagram on the energy scale, that's what we're showing here. So the other 2 ways that we can express electron configuration is the first one listed up here, which is an electron configuration list. And here we simply just write which orbitals have each number of electrons. And we write the value of electrons that are in it as a superscript. So we can say nitrogen has a 1s orbital with superscript 2 saying that there's 2 electrons in the 1s. So that talks about these 2 guys. Next we go 2s2. We're talking about the 2s orbital. And then we now go to the 2p, 1, 2, 3, 2p3. Okay, that's simple. Just talking about what is in each how many electrons are in each type of orbital at each energy level. Next, we're going to take a look at the orbital filling diagram, which is in the middle of the slide. And so basically, this is the same idea as the orbital filling diagram on the energy scale, except it doesn't have, obviously, the y part of it, the y-axis part of it of the energy scale. So you just write out a sort of pictorial representation of each orbital that's full. So we'll have for nitrogen, we'll have a 1s orbital, a 2s orbital, and then three 2p orbitals, and we'll just write each of these individual electrons into the orbitals. And so this would be the representation for the middle. So all three of these are all equal, and they are all acceptable forms of electron configuration. Okay, so how do you remember the order in which these orbitals arrange themselves and which they fill? So one way you can remember is, I think the easiest, is just by looking at your periodic table. So we have different blocks based on where how the table is oriented. Okay, so on the left hand, if you look at your periodic table, on the left hand side, the bit that goes up, this is the S block. So there's two different boxes here within the S block. And then, so the helium is going to come over here with hydrogen to join this complete S block here. And you can see that we have 7 different rows. Each of those has 2. So those are, if your element ends within that S block, those are going to be S orbitals. So over here on the right-hand side, where there will be 6 different blocks that make up the P block. And then this one here in the middle for our transition metals is the D block. And then our lanthanides and actinides, excuse me, are the F block, and there's 14 of them. Okay, and so as the order in which they flow, so you have our so the energy level 1 for S is our first row, so that makes it easy. And then for the second row, we have energy level 2S and then 2P. Then energy level 3S, then 3P, then energy level 4S, and then here's the sort of tricky part. You have to remember that the D block goes to 3D, okay? Instead of 4D, it actually goes to 3. So that's something you kind of have to memorize, and then it goes back up to 4P, and then we go to 5S, then again 4D, because we're 1 behind for the D block, and then 5P, and then 3S, and then that's where the F block would then pop in. So you go 4F, so that lags 2 behind our S group, and then 5D, 6P, so on, so on. And so we typically don't really consider elements that have these F blocks in there, but it's just good to know that they're in there. Okay, and so this arrangement of blocks actually helps us to remember that the swap in the order when filling the electron orbital filling diagram for the non-hydrogen atoms, for any of the multi-element atoms. And so you can see here that the 4s actually comes in energy level before the 3d, and then it goes to 4p. Okay, and so another way that some people like to remember how to fill the orbitals is if you put all of the S's, P's, D's, and F's, so you have all the energy levels laid out, and so you start to draw diagonal lines. So if we drew another diagonal, so you'd see the 1s goes first, the next diagonal says the 2s is next, then the next diagonal goes 2p, 3s, and then it goes 3p, 4s, 3D, 4P, 5S, so on, so on, so on. You could keep drawing those as well. So whichever sort of way helps you memorize the best. Really, once you practice it a few times, I think just looking at the periodic table would be the most straightforward for you. So let's take an opportunity now to take a look at the electron configuration of a few elements here. So I have all of the elements listed from 1 to 10, and then manganese, arsenic, and cadmium, just 3 other ones for us to practice writing the electron configuration for. So I insist that you guys pause the video and try to go through this on your own. And then when you finish, log back in, and we will work through it together. Okay, so when we go through these here, we'll start with helium. So the best way to do this is just to look at your periodic table. So when we have our periodic table here, you're going to be taking a look at just basically counting boxes. So remember, helium's going to come back over in our S block. And for each one, you're just going to look at the S block, the P block, the D block, and you're going to count them out, knowing that the first row is the energy level 1, second row energy level 2, third row energy level 3, fourth row energy level 4 for the S and P blocks, but that top row on the D block is an energy level 3. Okay, and you're simply just going to count off blocks, and that's how many electrons are going to be in each different orbital type. So for hydrogen being in the S block, we have one S, and there's only one electron. Helium, remember, we're moving that over next to hydrogen. That's going to be a 1s, and there's 2. All right, now lithium, we've completed the 1s, 2, and then we now move down to the 2s, and there's only 1. Now for beryllium, again, 1s2, 2s2. Next for boron, we know we're going to jump over until our P block now. So we have 1s2, 2s2, and now we have 2p1. Carbon, 1s2, 2s2, 2p2. Hopefully you can see the trend here. For nitrogen, we have 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. And for neon, we have 1s2, 2s2, 2p6. And then for manganese, we have 25. So we locate manganese on here, and so that's in our D block. So we know we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we enter our D block, which again is an energy level 3, and we just count 1, 2, 3, 4, 5. Okay, so that would be 3d5. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Arsenic, we take a look, so that's going to be 33. So that's over there. We get all the way through our 3s, or sorry, our 3d10, and then we head back to the 4. So this is 4p, 1, 2, 3. So 4p3 will be our last. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Okay, and finally cadmium. So cadmium is located at 48, so this is on the 4D, and that'll be finished at 4D10. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d10. Okay, so the good rule of thumb here is just to practice, practice, practice. And once you practice, this will really become some second nature for you. So you can see, especially when we get to these longer, the heavier sort of elements, the writing of these electron configurations can be quite cumbersome. So a nice little shorthand trick that we have is what's called the noble gas configuration. So if we switch over and do the noble gas configuration, the way that we write up the noble gas configuration for all of these elements is you take a look at your periodic table, and whatever noble gas comes directly before the row in which you're dealing with, that's what you start off with. Okay, so if I'm talking about sodium, number 11, I look for the noble gas immediately prior. So number 10 is neon. Okay, or if I'm talking about phosphorus, P. So I go to the previous noble gas, which again would be neon. And so what you do is you put in brackets what the previous noble gas is, and then you just start counting from there. Okay, so if we assign our noble gas for all of these guys, so hydrogen and helium do not have a noble gas beforehand, so we just list those at 1s1, 1s2. But for lithium, we take a look and see what's the noble gas right previous to lithium. It's helium. And so for that, we put helium in brackets, and then we start directly afterward to 2s1. So it's a bit of a shorthand. For beryllium, same idea, helium 2s2. Boron, helium 2s2, 2p1. Carbon, helium 2s2, 2p2. Nitrogen, helium 2s2, 2p3. Oxygen, helium 2s2, 2p4. Fluorine, helium 2s2, 2p5. And neon, so neon is a noble gas, so all we have to write here is simply neon. That's it. Manganese. So now we take a look. So manganese is 25. So we go and find the previous noble gas. So if we go all the way back, we see that argon, Ar. So that's going to be argon. And we look right past argon. The row we're going to start with is energy level 1, 2, 3, 4. So that'll be 4s2. Oops, sorry, I put that under the neon, right next to the argon, sorry. 4s2. Okay, and then for manganese, we're at 1, 2, 3, 4, 5. So that's 3d5. All right, arsenic, again, we look for the previous noble gas, which again is argon, Ar. And then we go again, 4s2, 3d10, and then 4p, and we count 1, 2, 3, 4p3. Much more straightforward. And then cadmium, we look for our previous noble gas, which is krypton, so Kr. And then we look, that next energy level is 5, so we go 5s2, and then 3d10. Oh, sorry, 4d10. Sorry about that, 4d10. Okay, so you can see this noble gas shorthand is much more easy to handle. Okay, so this figure here just shows the noble gas configuration for all of the elements on the periodic table. Okay, and so most all of them fill based on the off-ball principle and Hund's rule, they all fill as expected. But if you pay close attention, you'll see there are a couple cases where we have a few exceptions. So if you take a look here, you can see that chromium actually has an exception. It has a 4s1 3d5. And copper has a 4s1 3d10. So there are a few exceptions to the rule where the filling does not occur as expected. So some of the anomalies in electron configuration are shown here. So chromium and copper, like I mentioned, then molybdenum, Ru, Rh, Pd, silver, platinum, gold. All these guys have exceptions. So you should definitely be able to recognize the elements that will have exceptions. So let's think of reasons why these exceptions would occur. So let's look at chromium and copper, for example. Okay, so if we think about chromium first, okay, so the valence shell, so the most outer level for chromium is going to be 4s2, oh sorry, so the 4s energy level, and then the 3d energy level. So we have one orbital for the 4s, and we have 1, 2, 3, 4, 5 orbitals for the 3d. So the off-ball principle and our rules for filling up electrons would suggest that this would be the electron configuration. But it turns out the 4s and 3d energy levels are so close to each other, it's actually more energetically favorable to leave the 4s unpaired and put that extra sixth electron over in the 3d. And so this way you have a completely filled 3d subshell, and all of these electrons here have have the same spin orientation. Okay, so this is one of the anomalies. This is for chromium. Next one we want to take a look for is copper. So copper would suggest, so again, we're dealing with the same 4s and 3d. We would expect copper to fill like this, with the open energy state on that last 3D orbital. But we can see that this is an anomaly where the electron actually pairs up in the 3D and leaves the 4s unpaired. So it's actually more energetically stable to have a totally completely full 3D orbital in this case than it is to have a full 4s orbital. All right, so you can see the other anomalies are following suit. So that same sort of group here, right below chromium, we see molybdenum still has that same sort of anomaly. Silver, right below copper, has an anomaly, and also we see it here for gold as well. Okay, so those are some of the key groups that you should be able to recognize as being anomalies to the electron configuration rule. So this noble gas configuration that we're looking at here, if we recall back to our discussion of effective nuclear charge, we introduced the idea of valence shell versus core shells, where valence shell is your outermost shell, and then valence electrons are the electrons that are located in that outermost energy shell. And the core shells are all of the energy levels that are smaller than the valence shell. So if our valence shell is energy level 3, the n equals 1 and n equals 2 energy states are both core shells. And any core electron are the electrons located in any of these inner energy levels. And so important to note, these core electrons include the outermost d and f orbitals. Okay, so d and f orbitals will never be considered valence electrons. Okay, so we have our definition of valence versus core. This noble gas configuration that we put forth is really just writing your valence electrons. Okay, so it's a little bit of an exception to the rule if we end with a D block. So we do write the D electrons on there, even though those are technically not valence. You'll still write them with the noble gas. What's important to be able to recognize the valence electrons versus core electrons. Okay, so I ask you to work through this problem, pause the video and work through, to write out the electron configuration, both short and longhand, and the orbital filling diagrams for the following atoms. Identify the valence electrons and assign a full set of four quantum numbers to each of your valence electrons. Okay, so we have selenium, molybdenum, and sodium. Okay, all right, so we'll start off with selenium. So selenium, Se, that's going to be element number 34. So for writing out our notation here, we can see that this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4, 4p4. Okay, so that's the longhand notation. If we look at the noble gas immediately preceding selenium, it's going to be argon. So we can write this shorthand Ar, and then go forward from there, 4s2, 3d10, 4p4. Okay, so our valence electrons here are going to be the electrons in the outermost shell. So we would be talking about our outermost valence electron or shell would be our energy level 4. So our valence electrons would be all the ones in energy level 4. Okay, so those would be our valence electrons. Okay, and if we write our orbital filling diagram for this, we draw our energy scale. We have our 1s, 2s, 1, 2, 3 for 2p, 3s, 1, 2, 3 for 3p, 4s, and then we go 1, 2, 3, 4, 5 for 3d, and then 1, 2, 3 for 4p. And yeah, we'll fill up from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Okay, so just filling up the electrons from the bottom up. Okay, and if we're going to identify each of our valence electrons by our set of quantum numbers, first, if we take a look at this guy here, we're going to have an energy level of 4, so that's going to be n is equal to 4. This is the s orbital, so our L is going to equal 0. There's only one suborbital of s, so our m sub L would be equal to 0 for the s. And this is an upward spin, so our m sub s would equal plus 1/2. So this set of quantum numbers would talk about this specific electron. This electron here will have all of the same quantum numbers, except the spin would be opposite because it's spin down. So n equals to 4, L is equal to 0, m sub L will equal to 0, m sub S will equal to minus 1/2. So you can see that we show that two electrons, they have to have a set of 4 unique quantum numbers. Okay, now if we're talking about these guys up here, I won't work through all of them. I'll just work through one of them here for us again. If we take a look, I'll delete this up here to give us a little room. We would have an energy level of 4, so n is equal to 4. Our L for a p energy level will be 1. Okay, our m sub L can either be -1, 0, or +1. So I like to just keep them in order, so we'll call that +1. And it's an up spin, so we call that m sub S is equal to plus 1/2. Okay, this guy here would have all the same numbers, except the m sub L would equal 0. This guy here would have all the same numbers, but the m sub L would be -1. And then its neighbor would have the same numbers as its friend right here, but just with the opposite spin. Okay, and I'm not going to take the time in this video to work through molybdenum and sodium, but please let me know in class if you have any questions with that. Okay, so if we recall our atomic structure, so we have all of these different orbitals, and so these orbitals all arrange themselves around the nucleus to make a spherical atom. And the higher the energy levels that are occupied, the larger this atom extends. Okay, the larger the radius of your atom, the more filled orbitals that you have. So this leads us to thinking about the atomic radiance. So since there's no definite boundary of an atom, atomic radius is determined by the half distance between two identical atoms bonded together in a chemical compound. So for example, if we have two chlorine atoms that are bonded together, we take a look at the distance between the two, we divide that in half, that can give us the atomic radius of chlorine. Same thing for carbon-carbon. And you can see when you put those guys together, you can make a pretty good prediction about the actual atomic radius of a certain atom. So we have some periodic trends in when we take a look at the periodic table for atomic radius. And so these trends are important for you to sort of memorize and remember. Okay, so we see as we go from the top of the periodic table down towards the bottom, we can see that the radius of an atom increases. Okay, whereas if you go from the left of the table to the right-hand side of the table, we can see that the radius decreases. And now there are a couple reasons behind this change in radius. One of the first reasons that we're going to look at is the trend going from the left to the right. So as we go from the left of the table to the right-hand side of the table, the atomic radius gets smaller. So the reason for this is due to the effective nuclear charge. Okay, so remember that this is the quantification that tells us how strong of an attraction do the valence electrons feel from the nucleus. And so to calculate that, the effective nuclear charge is equal to the positive charge in the nucleus minus all of our core electrons, so the electrons that are shielding. And so we calculated in a previous class that as we are further on the left, we have a very small effective nuclear charge, but when we get over towards the right, towards the halogens, our effective nuclear charge gets much, much larger. So if we calculate the effective nuclear charge for all of the period 3 elements, we can see a general trend that carries on. So as we take a look at sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, so if we write down each of their numbers, so 11, 12, 13, 14, 15, 16, 17, and 18. So these are the number of protons in the nucleus. And then we subtract out the number of core electrons. So basically, the number of core electrons are going to be however many electrons are in the previous noble gas. Okay, so just like we identified the previous noble gas for the shorthand configuration, if you take a look, that noble gas for this row 3 would be neon. And we see that neon has 10 electrons, so that is an easy way for us to determine what the shielding is for each of these conditions. Okay, so we are subtracting out the 10 electrons that are going to be core electrons. And we can see here now very easily that our effective nuclear charge increases by 1 as we move from left to right on our periodic table. So what does this actually mean? So this means that the valence electrons are actually feeling much more of a positive charge when we get further to the right on the periodic table than they are on the left-hand side. So what that has the effect of doing is it contracts in those valence electrons towards the nucleus. So the higher the effective nuclear charge, the stronger the pull on those valence electrons towards the nucleus. And so what that has the effect of doing is decreasing the overall atomic radius. Okay, so let's include the effective nuclear charge trend onto this periodic table, just as sort of a reference for us. So we see on the left-hand side where we have our large radii, those are going to have a low effective nuclear charge. Atoms on the right-hand side are going to have a high effective nuclear charge. Okay? Next would be the atomic radiance, and this is a plot showing the atomic radius versus the effective nuclear charge. So we can see as the effective nuclear charge increases, the atomic radius here decreases. The second reason in which that can explain the trend in atomic radius that we see is just the amount of energy levels that are occupied by electrons. So as we go down the periodic table, we start with energy level 1, energy level 2, 3, 4, 5, 6. So the more energy levels that we actually are inhabiting with electrons, the further out those orbitals extend. So if we're talking about our alkali metals, lithium, sodium, potassium, rubidium, and cesium, they all have the same effective nuclear charge of 1, but they increase in their overall atomic radius because they're incorporating larger and larger energy levels. Okay, so our final slide here is a question for you. Which atom in each of the following pairs would you expect to be larger, and explain? Okay, so let's walk through each one of these. So I would pause the video and try to work through it yourself, but we can now walk through it together too. Okay, so if we're looking at magnesium, which is an alkaline earth metal, number 12, and then we have barium, which is an alkaline earth metal 56. So we're going to expect barium to be larger because it is an energy level 1, 2, 3, 4, 5, 6 whereas magnesium is an energy level 3. Okay? Now, if we take a look at tungsten, which is number 74, versus hafnium, which is 72. So what we notice here is hafnium is 2 elements to the left of tungsten. So therefore, it's going to have less of an effective nuclear charge. Therefore, the atomic radius of hafnium is expected to be larger than tungsten because that nucleus is going to be pulling in on tungsten more than it is on hafnium. Silicon is number 14. And if we look at tin, which is number 50. So the same sort of justification here. They both have the same effective nuclear charge of 4, but tin has a larger energy level than silicon, so tin will be larger. Lastly, we have osmium, which is 76. And then we have Lu, which I think is leucine, which is number 71. Same sort of justification here. Leucine has a lower effective nuclear charge than osmium. Therefore, leucine should be larger. All right, that's it for the day. Thank you.